So, welcoming all in my next lecture. So, this lecture my plan is to talk about tangent plane and normal line of a given surface. So, in my last couple of lectures I introduced the notions of suppose if I have a functions from Rn to Rm, then I introduce the notion of partial derivative, directional derivative, total derivative. Then of course, I introduce the notions of what is called gradient vectors, couple of examples, then sufficient condition for differentiability or total differentiability, necessary conditions for total differentiability, and then chain rule. So, only the part is remaining like application part. So, that is my plan is to discuss in this lecture. So, that means you will see that we will have like once I have the notions of differentiability of a functions from Rn to Rm, then there is a kind of, as I said, this tangent plane and normal line of a surface. What will be that concept? That is the plan in today's lecture. So, let me just recall that this chain rule I have already discussed in my last lecture. So, again just to recall what is chain rule, like I know the notions of differentiability of a functions from Rm to Rn. So, like look at the theorem, statement of the theorem. If I have a function say capital X from R2 to Rn, okay, and so since it is a R2 to Rn, so that means I will have n component functions, that is x1, x2, xn. Suppose it has partial derivatives at the point AB, that means partial derivative with respect to two variables, that means either u or v of the functions x1, x2, xn exist. And suppose if we have a functions f from Rn to R, suppose it is differentiable at the point y, which is x of AB, then you can talk about the differentiability of the composition functions. Here composition function means what? Capital F is a composition of f composed x. It is a map from where to where? It is a map from R2 to R. So, that means if I know the differentiability of small f and capital X, then I can talk about the differentiability of capital F, that are composition functions, that is the chain rule, and you will have a formula. So, if x is differentiable, if f is differentiable, okay, then I can talk about the differentiability of the composition functions capital F. So, statement is that, so if capital X has partial derivatives, if small f is differentiable at the point, then the composition function has partial derivatives at AB, and you can write the partial derivatives of capital F in terms of the partial derivatives of capital X and partial derivative of small f. And what is that? So, that means del f del u at AB, which is nothing but the gradient vector of f at the point y, which is x of AB, dot product with the partial derivative of x with respect to u variable at AB. Similarly, partial derivative of capital F with respect to v variable at the point AB, which is nothing but gradient vector of f, which is exists because my small f is differentiable at y, that means x of AB, dot product with partial derivative of x with respect to v variable at AB, and partial derivative of x with respect to u and v also exists because it is in the statement of the theorem, and that if I take the dot product, this is the corresponding expressions. So, now so this is called chain rule. If you see earlier, I think my earlier theorem, so I have a function x from R to Rn, and this time R2 to Rn, I have a composition functions. So, this is the formula, like if I have two functions, then you can easily calculate the corresponding partial derivatives in this way. Yeah. So, now this is the kind of part for this set of lectures, is that I want to talk about the tangent plane and normal line of a given surface. For that, let me just recall what do I mean by graph and level set. It says that let f be a functions from Rn to R. Graph of f, you know, I think all of you, graph of f is the collection of points. So, it is a collection of vectors, like first component is the x itself and second component is the f of x, that means range of f, where x running over Rn. So, if f is a functions from Rn to R, then graph of f is a subset of Rn plus 1. This is called the graph of f, and graph of f you can have a kind of picture in the n plus 1 dimensional things. Of course, it cannot visible, right, because more than its 3 dimension. So, graph of f represents a hypersurface in Rn plus 1. So, because if I have a functions from Rn to R, g of f, or that means graph of f, which is subset of Rn plus 1, and it represents a hypersurface in R to the power n plus 1. Once I have the graph, then I can talk about what is called SF alpha. Given alpha, I can consider the set SF alpha. What is that set? It is a collection of all those vectors in Rn such that f of x is exactly equal to alpha. Okay. So, if I consider this set is called the, of course, this is a subset of Rn first of all. This set is called the level set of F, and it also represent a hypersurface in Rn, not Rn plus 1. Look, it is a set subset of Rn. So, once I have a graph, then I can define a set for given F and given alpha. I am defining a set S F alpha, which is a collection of all those vector in Rn such that f of x is equal to alpha. That I am saying that is a level set of F, or and it represent a hypersurface in Rn, or sometimes I will say that this is a level surface. Given a functions f and alpha, S F alpha, I will say the level surface. So, one picture I have kind of taken. So, it is like, for example, this is a kind of graph of these functions f of x y is equal to square root of x square plus y square. So, that means if I take the graph of this thing, so that means if I take the point x y f of x y, so that means take x comma y and then f of x y. Okay. So, this will be a point in where? Point in R3, right. So, if I draw it, then it will be a kind of graph. So, this is the graph of the functions f square root of x square plus y square. Once I have the graph, then I can talk about its level sets or level surface. That means I should go one dimension less. So, this is a kind of hypersurface in R3. Once I will talk about the level surface or level set, or so then it should be one dimension less. That means it will be a something, some curve in R2. That means what will be the corresponding level surface or level curve, I should say, because this time actually I am one dimension less. That means I am in R2. That will give you the, I will say that is level curve. So, that is I have drawn it actually. So, level curve, that means you fixed a k, so square root of x square plus y square is equal to k, that means it is circle. So, that means for k is equal to 1, this is the level curve, k is equal to 2, this is k is equal to so on and so forth. So, that is very easy example. So, since I am taking examples from R2 to R, like f of x y is equal to square root of x square plus y square, that means the corresponding graph, it represents a hypersurface in R3, which is I just shown, this is the one. And once I talk about the level set or level surface, it will be a kind of, it will be in RT, and I am saying that it is a level curve. Okay, so now I am going to talk about what is level sets, because there is a connections between the gradients. Gradients I already talked about. If I have a functions from Rn to R or Rn to Rm, then I can talk about the gradient vector. And level sets, there is a connections, but what is that connection? Let me just check. So, let f be a functions from Rn to R. Suppose it is differentiable at the point x naught, and I know what is the meaning of differentiability, or that means the existence of total derivative. Suppose x naught is a point on the hypersurface f of x is equal to alpha. So, what I have a function f from Rn to R, and I assume that it is differentiable at the point x naught, and I am assuming that x naught is a point coming from the hypersurface f of x is equal to alpha. Then what I am doing, I am saying that suppose capital X is a map from minus epsilon to Rn, it is a curve on the hypersurface f of x is equal to alpha passing through the point x naught. So, that means what I have? So, I have a hypersurface, right. So, f of x is equal to alpha. So, given a function f from Rn to R, first I am considering, for given alpha I am considering the hypersurface f of x is equal to alpha. So, it will be a surface in Rn. Then I am saying that, okay, I am considering a curve capital X, which is a map, of course, is a parameterizations minus epsilon to Rn. That means it is a curve in the hypersurface, not in Rn. That means in particular it is a curve in the hypersurface f of x is equal to alpha passing through the point x naught. That means x of 0 is nothing but x naught, and since it is a curve in the hypersurface, that means it should satisfy this equation f of x is equal to alpha for all t from minus epsilon to epsilon. So, I have a functions f from Rn to R. I have a hypersurface f of x is equal to alpha. I am taking a point x naught, which is a point in the hypersurface, and then I am considering a curve on the hypersurface passing through the point x naught. Okay, that is kind of assumption I have. Now, look, what I am saying is that suppose my curve x, which is differentiable at the point 0. So, now I am starting with my functions f from Rn to R, which is differentiable at the point x naught. Then I am considering a hypersurface, and then I am considering a curve on the hypersurface passing through the point x naught, and then I am assuming that suppose that curve is differentiable at the point 0. Then if I consider this composition function f compose x, x is differentiable at the point 0, and x of 0 is what? X naught. So, that means what I am saying is that, so f compose of course, a capital X, I have one function capital X, I have another function small f, and I want to talk about the differentiability of the composition functions small f composition with capital X. Capital X, I assume that it is differentiable at the point 0, and x of 0 is x naught, and f is given to be differentiable at the point capital X naught. Then I can talk about the differentiability of my composition function f compose x at 0, because x is differentiable at the point 0. And what is the value of, so that means f of x0, what is that point? This is nothing but x naught. Now also small f is also differentiable at the point x naught is given. So therefore by chain rule I can talk about the differentiability of the composition function f compose x. So that means f compose capital X is also differentiable at the point 0. And what is the derivative? Because what is the f composition function? So t goes to f of x, or I should say f compose x at t. What is this? This is f of xt, okay, and since I am talking about my curve in the hypersurface, so it should satisfy this equation. This is exactly equal to alpha for all t from minus epsilon to epsilon, right? Now since small f is differentiable at the point x naught, capital X, the curve which is differentiable at the point 0, composition function is the is also differentiable at the point 0, and by chain rule I will have this expression. But on the other hand, if I take the derivative of the composition function f compose x, since it is exactly equal to alpha for all t lies between minus epsilon to epsilon, so what will be the derivative? Derivative will be 0. It is because constant functions, right, because I am in the hypersurface. But the composition derivative I can write in terms of the derivative of small f and derivative of capital X, that is by chain rule. And what is that? I already discussed. This is nothing but the gradient of f at x naught dot product with derivative of capital X at 0, that we know by chain rule. Okay. So the left hand side, because I am in the hypersurface, my curve is in the hypersurface at the passing through the point x naught. So the composition function is differentiable at the point 0, and since composition function is constant because I am in the hypersurface, so therefore derivative with respect to t at the point is equal to 0 vanishes 0. But it will have an expression in terms of chain rule, which is nothing but the partial derivative of f at x naught dot product with x prime 0. So that means what I am doing is that, so once I have this kind of set of assumptions, then I am saying that 0 is exactly equal to the gradient vector of f x naught dot product with x prime 0. In other words, the gradient vector is orthogonal to the vector x prime 0. So that's what I am saying. So that means if I have a function say from Rn to R, okay, and if I given a alpha, if I consider the level surface f of x is equal to alpha, if I consider a curve on the level surface passing through the point x naught, and if I assume that that curve is differentiable at the point 0, then using chain rule I am concluding that the gradient vector of f at the point x naught is orthogonal to x prime 0. Now note that since the line x naught plus t time x prime at 0 is the tangent to the curve xt at x naught, because x naught plus t times x prime of 0, it's a line, right? It's a line with gradient x prime of 0. That line, it's actually a tangent to the curve on the hypersurface at the point x naught. So that means I have a hypersurface, okay? So I have a curve, I have a point, and that I have a tangent, and that tangent, which is nothing but the line x naught plus t times x prime 0, which is a tangent to the curve xt at the point x naught. Okay. So that means I have a hypersurface, I have a curve, I have a tangent. Okay. Then since x naught plus t time x prime of 0 is a tangent with the gradient x prime 0, and I just observe that this gradient vector is orthogonal to that x prime of 0, then gradient vector at x naught is nothing but the normal to the hypersurface f of x is equal to alpha at x naught. Okay. So this is very nice actually. So I have a first function say from Rn to R, I have a hypersurface, I have a curve, I am defining a curve on the hypersurface passing through the point x naught, then I observe that the gradient vector at the point x naught is orthogonal to x prime of 0. But the line x naught plus t time x prime of 0, that means the line passing through the point x naught gradient x prime of 0, it's nothing but a tangent to the curve xt at x naught. And since gradient vector of f at x naught is orthogonal to x prime of 0, so therefore gradient vector at x naught is nothing but the normal to the hypersurface f of x is equal to alpha at the point x naught. Okay, so this is actually particular examples. I am saying the kind of notion of tangent plane and normal line to a level surface. I am kind of restricting myself on say 3 dimension. Let's see what is going on. Okay. So, let f be a functions from E subset of R3 to R. Suppose take a point x naught on the level surface. So, suppose capital X naught is a point on the level surface and this is my level surface S. What is my S? Is all those point x, y, z in R3 such that f of x, y, z is equal to C, where C is a fixed real number. Okay. So, that means given a functions f, I am considering the set S which is a level surface, okay, and I am assuming the point capital X naught is a point on the level surface. Let f be differentiable at x naught. I assume that suppose f is differentiable at the point x naught, then the tangent plane to the level surface S at the point x naught is a plane passing through x naught and normal to the gradient vector del f at x naught. Okay. So, just now I observe, that means if I have a level surface, if I have a kind of point x naught and if I take a curve, then the tangent is orthogonal to the gradient vector, right. So, now I am defining the tangent plane to my level surface S at the point x naught, and what is that? Is the plane passing through the point x naught and normal to the gradient vector del f at x naught. And now once I have I want the equation of a plane which passing through a point and suppose it is orthogonal to the gradient vector, then you can easily write the kind of equation of this plane. And what is that? So, this is nothing but, so you write the gradient vector of f at x naught. Okay, what is this? This is nothing but del f del x at the point x naught, del f del y at the point x naught, and del f del z at the point x naught, because I am in 3 dimensions. So, it is a point in R3, right. So, this is my kind of gradient vector at x naught. So, I want a equation of a plane which is passing through the point x naught and orthogonal or normal to the gradient vector. And what is the equation? This is nothing but, so it is the fx or partial derivative of f with respect to x at x naught times x minus x naught, partial derivative of f with respect to y at x naught times y minus y naught, plus partial derivative of f at x naught with respect to z variable times z minus z naught is equal to, that is very straightforward. If I have a function, if I want a equation of a plane which passing through a point and normal to the gradient vector, this is the equations. Okay. So, once I have the equations of tangent plane, then the normal line to the level surfaces at x naught is the line perpendicular to the tangent plane. So, now I have the equation of a tangent plane. So, I need the equation of a normal. Of course, the normal, it should be parallel to the gradient vector of f at x naught, and one can write by the following equation. What is that equation? So, x small x is nothing but x naught plus partial derivative of f with respect to x at x naught times t, y is equal to y naught partial derivative of f with respect to y variable at x naught times t, z is equal to z naught plus partial derivative of f with respect to z variable at x naught times t. Okay. So, what are the things? So, if I have a hypersurface, if I have a functions in suppose in from R3 to R. So, if I consider the level surface in R3, then I can talk about, if I take a point on the hypersurface, then I can talk about the equations of the tangent plane passing through the point x naught, and then I can talk about the normal line at the point x naught on that hypersurface. And this is the corresponding equations of the tangent plane, and this is the corresponding equation of the normal line. Okay. So, I kind of given a picture to understand pictorially what is going on. So, this is a normal line and tangent plane to a surface. So, what is my hypersurface in this setting? So, this is my hypersurface. So, this is my hypersurface. Okay. And suppose this is my point x naught. Suppose this is a point x naught. Okay. So, what is my tangent plane? So, this is my tangent plane. Okay. So, this is a round one. This is my tangent plane. Okay. So, this is the kind of tangent plane passing through the point x naught and normal to the gradient vector of f at x naught. Okay. And what is the normal line? So, this is the normal line on the hypersurface at the point x naught, that means it is perpendicular to the tangent plane. This is pictorially, I just kind of tried to kind of give the pictorial meaning of this normal line and tangent plane to a surface. Okay, one examples I have given, very simple example. So, what is the problem? Problem is that find the tangent plane and normal line to this surface at the point minus 1, 1, comma 1. Now, look how I solve the problem. So, the given surface can be written as the level surface. Okay, I can write it, because what is the surface? X square plus y square plus z square is equal to 3. So, I am saying that okay, that surface can be written as a level surface f of x y z is equal to 3, where f of x comma y comma z is nothing but x square plus y square plus z square. So, that means given a surface, I am just writing as a level surface f of x y z is equal to c, where I know the expression of f of x y z, then you can calculate partial derivative of f with respect to x, y and z at any point x, y, z. Okay, and but if we want to talk about the tangent plane or normal line to that level surface, then at some point, then you just evaluated that partial derivative at that point. Okay, so first you calculate fx, fy, fz at any arbitrary point x, y, z, calculate the corresponding point. That in that point I am talking about the equations of tangent plane and normal line. So therefore the equation of tangent plane is nothing but x minus x naught, which is x minus or minus 1, y minus y naught, y minus 1 times z minus 1, and then corresponding factor will be partial derivative of f with respect to x, y, z at the point minus 1, 1, 1, and this is nothing but minus 2, 2 and 2, and this is the equation. So equivalently this is the equation. What will be the normal line? Again, you just calculate the partial derivative of f with respect to x, y, z, evaluate at the point minus 1, 1, 1, and just use the formula x is equal to x naught plus partial derivative of f with respect to x at the point x naught times t. So that means this is the value minus 2, okay, minus 2 times t. This is the corresponding equations of the normal line to that surface. So that means if I have a given a surface, think about or write it as a level surface and just use the formula I have discussed in my last slides. There is another thing. So this is tangent plane and normal line for a given surface. So this is the formula I have given. Okay. So suppose you have a given a surface z is equal to f of x y. Okay, suppose this is given, and then you would like to find, okay, what is the equation of tangent plane and normal line of this surface at a given point. How do you do that? Okay, so first what you have to do, so equation of the surface is given, this is z is equal to f of x y. So now I want to write this surface as a level surface. Okay, what I am doing, so that can be written in the form what you do, f of x y minus z is equal to 0. Okay, right. So therefore the surface z is equal to f of x y is also the level surface capital F of x y z is equal to 0, where capital F is a functions given by this. So the given surface z is equal to f of x y, first I am writing that surface as a level surface. How I can do that? So just z is equal to f of x y is given, take z minus f of x y is 0. So write that this is capital F of x y z is equal to 0. This is the level surface of the functions capital F, right? This is a level surface, capital F of x y z is equal to 0, and what is my capital F, which is nothing but f of x y minus z. Now once we have the level surface, then you know the formula, what is the definitions of tangent plane and normal line at a given point. So that's what you have to do. So if I take a point capital X naught on the level surface, that means on the surface z of f, z is equal to f of x y, and suppose fx, fy are continuous at the point x naught, y naught, then the tangent plane to the surface S at x naught is the plane, this one, right. So that means if I have a point x naught on the level surface or on the surface z is equal to fxy, and suppose fx and fy are continuous at the point x naught, y naught, then the tangent plane to the surface S at x naught is the corresponding plane. And how do you get it? You can simply, because you know the level surface, and what is the formula? If you can see the formula for the equations of the tangent plane for the level surface f of x y z is equal to 0 at the point x naught, what is the definition? Definition is that del f del x at the point x naught times x minus x naught plus del f del y at the point x naught times y minus y naught, and del f del z at the point x naught times z minus z naught is equal to 0. That was the equations given. But what is capital F? Capital F is this one, it is given, capital F is equal to small f x y minus z. So therefore if I take the del f del x, then what will happen at the point, say, capital X naught, then what will happen? So del f del x means what? So that means this should be small del f del x, and z I can think about as constant, this will give you 0. So that means this is nothing but del f del x at the point x naught y naught. So that is, so that means del capital F del x at capital X naught is nothing but del f del x small f. So partial derivative of the small f at x at the point x naught y naught. So that's the relations. So that means partial derivative of capital F with respect to x variable at the point capital X naught is same as the partial derivative of small f with respect to x at the point x naught y naught, because your capital F is given by this equation. That's why. Similarly, you can calculate your partial derivative of capital F with respect to y variable at the point x naught, y naught, z naught, which is nothing but partial derivative of small f with respect to y variable at x naught, y naught, right. And what will happen with the partial derivative of capital F with respect to z variable at the point x naught, y naught, z naught? because I can think about this as a constant function. So, that means what, this is be actually minus 1. Okay. So, that is why your partial derivative of capital F with respect to x at the point x naught, which is this one, this is nothing but this value. Partial derivative of capital F with respect to y variable, which is nothing but del small f del y, which is nothing this one. And what will partial derivative of capital F with respect to z variable, minus 1, that means minus 1 is coming, and this is the corresponding equation. And similarly, you have the equations of the okay, this is equivalent. So, that means here what I am doing is that I am taking z in the right hand side, and this is the corresponding equations of the tangent plane of the surface z is equal to xy at the point capital X naught. So, this is the equations of the tangent plane, and then of course, you can talk about what will be the equations of the normal line, because once you can easily do that, right. Once you know the level surface and you know the partial derivatives of that level surface with respect to x, y, z at that point, then you know the equations of the normal line. And what is that? This is the one. Okay. So, the normal line to the surface S at the point P naught, okay, P naught means x naught, I should say, this should be typos, x naught, which is nothing but x naught, y naught, z naught. And what is that? This is nothing but x is equal to x naught. Then if you remember what is the formula, partial derivative of capital F with respect to x at the point x naught, y naught, z naught times t, and which is nothing but partial derivative of small f with respect to x at the point x naught, y naught times t. Similarly, you will have y is equal to y naught partial derivative of small f with respect to y variable at x naught, y naught times t, and of course, z is equal to z naught plus partial derivative of capital F with respect to z variable at the point x naught, y naught, z naught times t, but which is exactly equal to minus 1. So, therefore, this is z naught minus t. So, therefore, if I have a surface, given surface, suppose z is equal to f of x y is given, and if I ask that, okay, what will be the corresponding equations of tangent plane and normal line at a point x naught in that surface, then this is the corresponding formula for the tangent plane and normal line. So, some of the problem I can give in, and if, so that means how you achieve this formula, nothing. So, what given surface is given, z is equal to f of x y, you write it as a like level surface. So, that means define a saying that, okay, so my level surface is capital F of x comma y comma z is equal to 0, and what is my capital F? Capital F is nothing but small of f of x y minus z, that is the surface is given, and use the formula, then you will have the corresponding equations of the tangent plane and normal line. So, one example I have given. What is the example? Find the equations of the tangent plane and normal line to the surface this at the points say P naught 1 to 4. So, what we have to do? So, the formula is given, of course, the in terms of, so you just calculate. So, right, in that case, what will be your f of x y? So, you write first z, so this as f x y. So, that means I can write it as like say z is equal to f of x y, right. And what is my f of x y? F of x y is nothing but 9 minus x square minus y square, that is it. Once you have the small f, then you calculate the partial derivative of f with respect to x with respect to y, right. So, I can have f x, I can have f y, okay. And now you just calculate the value of the partial derivatives at the point 1 comma 2, and this is once you know the partial derivative of f with respect to x y, you can evaluate at point 1 2, this is minus 2, this is minus 4, and the given equations will be just put it in the formula that I just achieved in my last slides, and this is the corresponding equations. And similarly, you have the equations of the normal line, because you do not have to care about that, because it is a 1 2. So, that is exactly I have written. So, even if I am talking about x naught, y naught, z naught, but the formula stands out will be z is equal to z naught plus partial derivative of small f with respect to x variable at x naught, y naught times x minus x naught, then partial derivative of y with respect to y variable at x naught, y naught times y minus 1. That you just perform that you just do the calculations, get the partial derivative of f with respect to x and y variable at the point, if the point is given 1 2 4, just take the first xy coordinate, okay, evaluate it at 1 2 and use the formula, then you will have the equations of the tangent plane and the normal line. So, this kind of problem you can do as an applications, like what will be the corresponding equations of tangent plane and normal line given a point in the hypersurface or in the surface z is equal to f x y. So, that is all about like what I said in this lecture. So, that means till now, if I summarize everything what we have learned first of all, given a functions f from Rn to Rm, three cases, three set of functions I have defined. One is the real valued vector valued functions of real variable, then real valued functions of vector variable, and then vector valued functions of vector variable. And now for the case when I talked about vector valued functions of real variable, then you will have a very easy way of definitions of derivative that you are familiar with for real valued functions of real variable in that setting. That means for vector valued functions of real variable, corresponding definitions will be, you can easily take out. Then couple of examples I have given. Second set, when I have a like scalar field like real valued functions of vector variable, there you will see, or I introduce the notions of what is called partial derivative and directional derivative, and of course those partial derivative and directional derivative also in some sense you can think about it is like one dimensional derivative. That means derivative of real valued functions of real variable, because anyway even if I am starting my functions from Rn to R, but somehow I am looking at the functions in one variable, that means I am restricting in one direction. That means I am thinking about a functions from R to R and talk about the differentiability. However, when I am going to talk about the existence of total derivative, there it is a huge difference. That means you cannot have the extension of the usual definitions, because in Rn the division does not make any sense. Then I had to interpret my classical definitions for real valued functions with real variable in a way so that I can extend those concepts in the setting of real valued functions of vector variable. So I interpret that as a linear transformation, the derivative of real valued functions of real variable, I think about the derivative as a linear transformation, and those concepts I extend to the real valued functions of vector variable. And when I will have a functions for vector valued functions of vector variable, then it's very kind of straightforward in a sense that once I have a vector valued functions of vector variable, you just write it as a component functions. Each component functions is nothing but the real valued functions of vector variable, and you know the notions of total derivative in that setting, and there is a theorem that the existence of the total derivative of a functions from Rn to Rm, that you can think about, that I have defined as a linear transformation. That means it gives a linear transformation. Along with that, limit h goes to 0, norm of f of x naught plus h minus f of x naught minus the linear transformation acting on h divided by norm h, that should go to 0, right? If this is true, then I will say that my functions Rn to Rm is differentiable at the point x naught, and derivative is nothing but the linear transformations. And that you can talk about in terms when I am writing f as a component function, that component functions again a scalar field, and that's total derivative also exists, and this is vice versa. And then many kind of results we know, like what is called sufficient conditions for differentiability. A couple of examples we have seen, like existence of partial derivatives and total derivatives will not imply the existence of the total derivative or just differentiability. However, if you give some sufficient condition, that means if I assume the existence of partial derivatives along with the continuity, then it will implies that my function is differentiable. Okay, so those kind of theorem we have observation we have seen, and then we have the existence of gradient vector once my function is differentiable. Then we have see the corresponding algebra of differentiability, and then of course the chain rule we have seen. That means if I have two functions, then when can I talk about the derivative of the composition function? That is nothing but the chain rule, and various formulas we have seen. Okay, and at the very end we have seen like that some applications, of course some applications for vector valued functions of real variable I have given, and at the end I have talked about like if I have a surface say z is equal to f of xy, then what is the notion of tangent plane at the point x naught in the hypersurface and the corresponding normal line. What will be the corresponding equations? That's also I have discussed, and couple of examples, very easy examples. Once you know the formula, you'll be able to conclude. I think that's all for the time being. Okay, in my next lecture I will talk about like mixed derivative, and there are a couple of things will be there like mean value theorem, Taylor's theorem in the multivariable setting. So those are the kind of part I think I should discuss in my next lecture. So this whatever I have said, so I have just talked about existence of partial derivative, direction derivative, total derivative, tangent plane, normal line. So these are the things here. Of course chain rule. In my next lecture I will talk about mixed derivatives and some kind of theorems regarding mixed derivatives, and then mean value theorem, and then we'll have Taylor's theorem. So those are the concepts I will discuss in my next lecture. Okay, thank you.